everyone. This is Arnab Mohammed. This presentation is about the final report of fiber optic sensors. It says about the introduction of fiber optic sensors and application and advantages. The assignment 1 is based upon the challenges in generator temperature monitoring, the predictive scattering and its working and principle. Then the assignment 2 is based upon the importance of temperature monitoring in power transformer, sensing mechanism and experimental setups and what are the future works on it. Then the third assignment it says about the evolution of DFS, advanced network advanced network for the telecommunication, digital coherent sensing technologies. And the last one is conclusion and reference. The first assignment is it's about the gas cooled application of fiber optics distribution strengths and the temperature sensors. It is a cutting edge innovation aimed at improving how we are monitoring and maintaining the gas-cooled generator to ensure the reliability and safety. The main objectives of this work is to explore the use of fiber optic distributed sensors to enhance the temperature monitoring in gas-cooled generator. The overheating and the insulation degradation are critical issues that can lead to failure, and our main motto to address these challenges with a more effective solution. Some of the key challenges are here. The generator are designed with laminated steel plates which are insulated to prevent any current. However, this design is prone to overheating and the insulation breakdown, which if not detected earlier, it will cause a severe damage. The traditional resistant temperature detector that is RDS are commonly used for this, and it also carries some limitations that they will provide only data at specific points and require extensive wiring. And the advantages of fiber optic sensors. Here's the fiber optic sensors a game changer in the scenario. They allows for distributing temperature profiling across the entire generator, unlike the point-specific data provided by RDS. Additionally, they are immune to electromagnetic interference impacts and reduce the wiring complexities, making them highly efficient. It has numerous advantages. The fiber optic sensors offers continuous and comprehensive monitoring for temperature, ensuring even minor changes are detected in real time. The compact designs also ensure reliable operation in environments with high electromagnetic interference, which is offers a concern with traditional methods. In practical application, these sensors are installed at the straighter edge within the generator. This setup allows for real-time temperature profiling, which is crucial for early detection of potential failure, ultimately improving the operational reliability and safety. The predictive shift, a change in the light frequencies occur due to energy transfer during the interaction. This shift is based, it's dependent upon the temperature and the strain. This is the working principle of this. The predictive scattering. Let us deal with the working principle of this sensor. The predictive scattering is a process which light interacts with the material of fiber optic cables, and the frequencies of the scattering light shift based on the temperature and the strain. This enables precise distribution measurement. This is how predictive sensors work. The system consists of components like laser, pulse modulator, and circulator, and on the optical receiver. The optical pulses are sent through the fibers, and the reflective signals are analyzed to determine the locations and conditions of the hotspot within the generator. Then here how its system operates. Then the optical pulses interacts with fiber material, creating reverse signals and by analyzing the time and frequencies of this return signal, we can exactly precise data about the temperature and strain at different points along the fibers. Then the strains and the temperature isolation. An important consideration is isolating the effects of strains and the temperature, as both influence the predictive frequencies. This is done using the two fibers One of that measures the temperature only and another one that captures both temperature and the strain. By comparing the two, we can isolate and accurately measure these parameters. The fiber uh, then these are the two main methods used. One is the BOTDR, that is the Bredicchio optical time domain reflectometry, and the second one is the BOTDA, that is the Bredicchio optical time domain analysis. The BOTD is a single end access which is simpler but has a lower sensitivity and a resolution. In contrast, BODA uses a dual end access offering higher sensitivity, evolution and extended range, making it more suitable for critical applications. The generated test result. When testing the result, we are improves the distributor sensing profiles, that is BSP, aligns closely with the airfoil temperature, while RTD shows the higher localized reading. This highlights the accuracy and reliability of fiber optic sensors in the real world scenario. The spatial resolutions is another key advantage. That sensors can detect a hotspot as small in 1 centimeter and 1 kilometer fiber, ensuring the precise localization of faults and enhancing the maintenance strategies. The hydrogen cooled generator, the performance of these sensors are also has a validity and high validity in hydrogen cooled environment, which are high stress condition. This demonstrates their robustness and reliability under the various operating conditions. The conclusions of this is the fiber optic sensors offers a superior alternatives of RDX, improving the real-time comprehensive temperature monitoring. Its reliable results and particularly advantageous under the dynamic operating conditions. Assignment 2 is based upon the low-cost optical fiber-based temperature sensors for real-time health monitoring of power transformer. The importance of temperature monitoring in power transformers. Let us start by understanding why the temperature monitoring is critical in power transformer. The overheating can lead to the insulation breakdown and transformer failure. Then the significantly impacts the power system reliability. The current sensing method face challenges such as high cost and susceptibility to electromagnetic interference, making the case for the better alternatives. Then the objectives is here to develop the low-cost optical fiber-based temperature sensors. These sensors needs to be immune to electromagnetic interference, lightweight, corrosion resistance, and the capability of distributed sensing to ensure real-time and long-term reliabilities. Then the advantages of optical fiber sensors. Optical fiber sensors have several advantages. They utilize localized surface plasma resonance (LSPR) with functionalized optical fibers, typically coated with gold silica thin films. These sensors are highly sensitive to temperature-induced changes, ensuring precise and reliable measurements over a wide range of applications. Then the sensing mechanisms involve high sensitivity setups using a white light source and spectrometer. These systems detect changes in light signal caused by the temperature variation. It operates within a temperature range of 30 degrees Celsius to 100 degrees Celsius, providing the consistent repeatability results. Then the experimental setups. In the high-cost experimental setups, a white light source and spectrophotometers are used. While the providing excellent accuracy and sensitivity, this setup is 1Z, which can limit its scalability for widespread development. Then the experimental setups were by using the low-cost configuration to overcome the cost challenges. A low-cost configuration was developed. Here, the white light source is replaced by the green LED, and the spectrometer is substituted with the optical power meter. Despite these changes, the setups delivers the comparable accuracy, making it a valuable solution for the large-scale applications too. Then the field variations. The sensors was valid in the field by testing it's an energized transformer for over 160 minutes. The result shows the real-time temperature rise monitoring with high accuracy demonstrate the sensor reliability and particular and practicability in real-world conditions. Then the cost. This slide is about the cost comparisons for this. The proposed optical fiber sensor for the cost less than is 100. Then the traditional optical system cost is around 1,000. Then the electronic system cost is about around 40,000. Then this significant cost reduction makes the solution highly attractive for the power transformer. Then proposed the proposed improvements. The proposed improvements include using the commercial availability of LED and the photodiodes to further low cost. Additionally, the simplifying the designs will ensure the feasibility to large scale field development, making the technology accessible for the broader applications. Then the results and the future work. In summary, the proposed sensors provides reliable and repeatability temperature sensing comparable to the high cost system. In future works will focus on the development of field ready prototypes and integrating the cost effective detection system to modernize the transformer health monitoring affordability. Assignment 3 is based upon the digital coherent sensing over deployed fiber for advanced fiber telemetry. The introduction says about the distributed fiber sensing, that is DFS. DFS over the year, DFS has evolved significantly and is now utilized in telecommunications, the urban infrastructure monitoring and the disaster prevention. However, the challenges like big data handling, high hardware costs, and noise management remain key issues to address in this. Then, the overview of coherent MIMO-DFS. The coherent MIMO-DFS are nothing but multiple input, multiple output distributed fiber sensing. Is an advanced technique. It uses a robust integration method with the benefits such as polarization, diversity, and constant power interrogations. These improvement ensures the system is highly reliable and effective even in the complex environment. Then, the technology challenges. Despite its potential, DFF faces technological challenges too. For instance, polarization fading and phase noise can dispute signal integrity. The another challenges in integrating the sensor's capability with existing communication channels. Addressing these issues is critical for DFS to achieve its full potential. Then, the smart size and the network protection. In a smart size, DFS plays a pivotal role in monitoring urban infrastructure and ensuring network protection. It supports global network telemetry system, providing real-time data for proactive management of infrastructure health and the disaster prevention. And the next we are moving into the performance of coherent MIMO-DFS. The performance matrix for coherent MIMO-DFS has been evaluated on optical network, that is SNR. The signal to noise ratio measures and the co-propagation sensing signals have demonstrated the system efficiency in maintaining high signal over a long distance. Then deployed fiber sensing trials. A notable trials was conducted using the multi-core fibers in Italy. This field studies showcased the ability to map phase variation and measure distributed sensing parameters using real-world conditions. These results highlights the robustness of the technologies. Then the field condition and the threats. The fiber deployed face diverse environmental conditions, including aerial, buried, and urban setups. They are also exposed to the threats such as construction activities, natural disasters, and the DFS provides yearly warming system to address these risks effectively. Then the network telemetry and event identifications. The network telemetry is further enhanced to tools like Jones matrix and a backscattering signal matrix. The AI integration plays a crucial role here. Automatic pattern recognition for events such as fiber cuts and fiber cuts or intersections, significantly improving the response time. Then the event analyzer is supposed to give some examples of DFS can detect and analyze events like instructions, attempts, or impacts. Then with time frequencies analysis, these events are precisely identified, providing actionable insights for network maintenance and the disaster management. Then the future outlooks and the conclusions. Looking ahead, the advancements in the polarization diversities and the outcomes of this field experiments promise to further enhance the DFS, that means the scanning systems with space division multiplexing, that is ASDM, is another promising advance. Then, however, adapting these systems to diverse environments and fiber types remains a challenge we must overcome. In conclusion, DFS continues to hold great promise for transforming the network telemetry and smart infrastructure management. Thank you. Then these are the reference of those topics.